This video will describe how to solve problem 724 using Excel and Solver. This problem was the subject of the executive summary report from the last lesson. In the spreadsheet, I've got a problem statement. An investors club would like to divide investment dollars between two stocks, Louisiana Gas and Power and Trimex, with the smallest allocation necessary to achieve minimum targets for short-term growth, intermediate-term growth, and dividend rate. As with any problem that's done graphically, we want to identify the problem formulation for the linear programming problem. The decision variables are the dollars invested in Louisiana Gas and Power, and the dollars invested in Trimex. The objective function is always a function of the decision variables. In this case, we want to minimize the function x1 plus x2. x1 plus x2 is the function that gives the total dollars invested. This is a very simple objective function. The constraints are always stated in terms of the decision variables. Here, the first constraint is on short-term growth per dollar. So we'll have 0.36 times x1 plus 0.24 times x2 is greater than or equal to 720. The next constraint is on intermediate term growth. 1.67 x1 plus 1.5 x2 is greater than or equal to 5,000. The third constraint is on dividend rate potential. So it'll be 4% times the dollars invested in Louisiana Gas and Power plus 8% times the dollars invested in Trimex, and that has to be greater than or equal to 200. We also always have the non-negativity constraints. So we'll always write out a problem formulation, even on problems we won't solve graphically. Now we want to move to using Excel and Solver for determining the best investment. In the worksheet here, I have a template set up. Each column represents a decision variable, and the third column is the requirements. And then the values highlighted in blue are simply the inputs or assumptions for the problem. I'll set up cells for the decision variables. For x1 and x2, and I will go ahead and simply just enter starting values. I'm using 1,000 for each decision variable, and I always like to highlight the decision variables in yellow. And in this case, we know that the objective function is the sum of these two decision variables. So keep in mind that the 1,000 entered as in the decision variable cells for x1 and x2 is simply an arbitrary value. You can start with any value in these cells. I'm going to highlight the objective function with an orange color. I like to highlight the decision variables in the objective function consistently in all my models in the same color so that when I'm working with Solver, I know where to find these values. Now I need to put lines to accommodate the constraints. On the left-hand side of each constraint, we're going to calculate the total short-term growth for each stock separately, and then add this together to get the total short-term growth provided by the selected portfolio. So in this case, I want to multiply the decision variable value times the assumption for short-term growth for X1. In a minute, I'm going to copy this formula. And if I do this the correct way, it can be very easy to copy and paste. I'm always going to reference the decision variable from line 6, so I've got a $ in front of the 6. If I were to copy this formula down, however, I would want to reference the next assumption for the next constraint. Also, I may want to copy this formula to the right, so I'm not going to put a $ in front of the B. In fact, if I copy it to the right, I want Excel to change the reference to column C. So let's look at what happens when this is copied to the right and down. When I copy this formula to the right, it still references row 2 and row 6, but the reference on the column has changed to C. If I copy this cell down, notice the reference on the decision variable has not changed from row 6, but the reference to the assumption up top has changed to row 3. This is what I want because the row that I'm on now represents the intermediate term growth. I can continue copying this down and to the right, and the rest of the formulas will be correct. What I need to do is to add, for instance, the short-term growth for this portfolio from the two stocks together to get the total short-term growth potential for the entire portfolio. I need to do something similar for the other two constraints. So the values that are highlighted right now are the total requirements calculated for the portfolio. I'm going to insert a couple of columns here so that I have room for the rest of the model. I know that these left-hand side totals have to be greater than or equal to the requirements. I like to type an inequality into the spreadsheet. This will not actually do anything in Solver, but it does remind me where the constraints are on the spreadsheet. I reference the requirements from up at the top. I'm prepared now to go into Solver to set up this problem. In Solver, I need to set an objective cell. The objective cell here is the total amount invested, which is in D6, and which I've shaded with an orange color. I want to minimize that objective cell. The changing variable cells are also called decision variables. These are the things that the manager can adjust, or the investor in this case. I highlight the two cells for dollars invested. Next, I need to enter the constraints. The constraint window is in the middle of the solver box, and we can add, change, or delete constraints. In this case, I'll add. There are three constraints here, but since they are directly next to each other on the spreadsheet in a column, and they have the same inequality, I can enter these into one constraint box in Solver. So in the left-hand side, I'll highlight these three cells. That's the total left-hand side of the constraint. Use the drop-down to change this to a greater than or equal to constraint. And then highlight the right side. While we're in one solver box for the constraint, Solver will consider this as three separate constraints. The box here that says make unconstrained variables non-negative should be checked. That handles the non-negativity constraints automatically. The solving method for our problem will be simplex LP. LP stands for linear programming, as you're aware. This completes the solver setup for this problem. If you click Solve, Solver comes up with a window that says it found a solution. We'll choose the option to keep that solution. I'm also going to highlight sensitivity over here in the reports section before I click OK. While I'm not going to use this immediately, we will often want to use this sensitivity report to do some analysis of the solution to the problem. When I click OK, the sensitivity report will be placed on a separate tab of the Excel workbook. So the problem is solved. The optimal allocation is about $1,359 to Louisiana Gas and Power and about $1,821 to Trimex. If we look at the solution, we see that the intermediate term growth rate and dividend rate are met exactly. Those constraints are binding constraints. They are limiting the allocation that we can make here. We have more short-term growth than is required, so we would say that this constraint has slack. Notice that the sensitivity report is in the other tab of the workbook now. This completes the Excel setup and Solver setup for problem 724.